Okay, class, welcome to the first lecture of CHE 461, Process Control. In this lecture, I will give you an introduction to process control through an example that we've seen before. Let's start this class with a quote from Abraham Lincoln that pertains to process control. If we could first know where we are and whither we are tending, we could better judge what to do and how to do it. So this quote motivates the study of process dynamics, which we spent all of last quarter studying, in order to control and harness a process so that we know what to do when a controlled variable is upset. So let us introduce ourselves to process control through studying our familiar salt mixer. So here we have pure water that's flowing in the tank at a flow rate of Q, volumetric flow rate, and then also flowing in the tank are solid salt granules. And it's assumed that when these both fall into the tank and mix together, and it's well mixed, you know that because of the propeller, that the salt immediately dissolves in the water. And then out comes salty water. And the concentration of salt in the exit water is C. Now, it's desired to maintain the salt concentration C at a certain set point, i.e., we desire the salt water coming out of the tank to have a certain concentration of salt. It is desired to maintain the exiting salt concentration at a set point. At a set point. So the set point is the value of the concentration that we want to maintain it at. And this is difficult to do because the size of the salt granules, they're highly irregular. And so the mass flow rate of salt W is also highly irregular. It's a function of time and it's unpredictable. And that's what makes it difficult to control the concentration of salt. So we'll write that down. So incoming salt flow rate W and we'll explicitly write it as a function of time. It's changing. Is highly irregular. And that makes it challenging to maintain C at the set point. Okay, so let me make this a bit smaller. Okay, and another thing to note about this setup is that there's a control valve on the pure water coming into the system. So you can see the control valve right here. So it has this little bell on top of it, and that is a control valve. So what we aim to do is adjust the flow rate of the water coming in to compensate for changes in W. So a control valve allows adjustment of flow of pure water. And we would want to do this to compensate for fluctuations in W. So consider a case where we see a sudden increase in W. That would cause the water to be way too salty, right? And then what we would do then is to offset that increase, to compensate for it, we would increase the flow rate of pure water because that would dilute the solution and make it less salty. So the question is, for a given WT, how do you adjust Q in order to maintain C at its set point? And that's a central question in control theory. And obviously, in order to answer that question, we need to know something about the dynamics of this process. And that's why we studied process dynamics and CHE 361. Okay? And so with this setup, we can move on to describe the controlled, manipulated, and disturbance variables. And before I do that, I want to provide a quote that illustrates what a set point is in a more elegant way than I can provide. So this is a quote from a textbook. Important variables that have been selected to receive the attention of the control system. So this important variable would be C, right? The salt concentration coming out, how salty it is. That's the important variable that has received our attention because we want to control it. And this variable, it has target value at which we are required to maintain it at. And so these target values are called set points. So for example, a set point might be, and I'll decorate with SP to be set point. Let's see what the units were. They were grams per liter. So it might be something like 1 gram per liter, right? That could be the set point, right? And you want to maintain the salt concentration coming out of the tank at that. So that's a more elegant way to describe what a set point is. Okay, so with that, what are the controlled, manipulated, and disturbance variables for the salt mixer? Okay, so I've already sort of told you that the important variable that we want to control is C, which is the concentration of salt. So C of T, C of T is the controlled variable. I suppose it's a bit distracting to put that function of time there. It's not really needed. It is generally a function of time, though. So C is a controlled variable since we desire to maintain it at a set point. So C is the control variable. So that's a sort of definition of a control variable. It's a variable we want to control and maintain it at a set point. So the manipulated variable here is Q, because what we're doing is adjusting the flow rate of water via this control valve here in order to compensate for changes in W. So that's what we're manipulating. So Q is the manipulated variable. Give this one a nice underline too. Since we manipulate it via the control valve, as a means to indirectly adjust the controlled variable. And compensate for changes in the disturbance variable. So I already told you what it is. It's W, which is W. So when our disturbance variable, which is W, the salt flow rate, upsets our process and changes the control variable, then we would try to compensate for that change by adjusting Q. So it's the manipulated variable. And that's what a feedback control scheme would look like. So W is the disturbance variable. It's highly irregular, fluctuates, and it's not controlled, it's not manipulated. Okay, we'll give this an underline too. So W is a disturbance variable because it fluctuates, it's not controlled or manipulated, so it's a sort of process of elimination thing here. And there's an additional feature, so that's not enough for it to be disturbance variable. It influences the control variable. So if this disturbance variable, or if this W did not influence the salt concentration, then we wouldn't really care about it and we wouldn't call it a disturbance variable. So it's not controlled or manipulated and influences the control variable. For example, the temperature is probably not a strong disturbance variable because the temperature doesn't really affect how salty this water is, assuming that it doesn't cause the salt to precipitate out or something like that. But that's why we need this last part, how it influences the control variable. And so I will give you a practice problem where you can identify the controlled, manipulating disturbance variables in different contexts. And so now let's talk about feedback and feed-forward control in order to maintain C at its set point in the face of the disturbances in W. So the key difference in feedback and feedback control is which variable you measure in order to know what action to take. So in feedback control, and I'll underline these to keep consistent with my definitions. So in feedback control, we measure the controlled variable. Okay, we measure the controlled variable. And the control variable here would be the salt concentration. And then based on the measurement of the salt concentration, based on the measurement of the control variable, we then adjust the manipulated variable on the basis of this measurement. So then we would adjust the flow rate of pure water based on that measurement. On the basis of this measurement. And how exactly you adjust it, well, that's what this class is all about. So basically, how much do you open that valve to let in more or less water to compensate for changes in W? That's what we need to figure out in this class. And it's really a mathematical question. So in feed-forward control, instead what we do is we measure the disturbance variable. And then still, we adjust the manipulated variable based on the measurement of the disturbance variable. So I can copy and paste this stuff down here because it applies here as well. Yep. So the key difference, so I'll use yellow. The key difference is that in feedback control, you measure the controlled variable, which would be how salty the water coming out of the tank is, and then take action based on that. Open or close that water valve based on that. Feed-forward control, we measure the disturbance variable, which here would be the incoming flow rate of salt, and then take action based on that, still adjusting that control valve. Okay, so this is what a feedback control strategy would look like in our salt mixer. So remember, feedback control strategy, we measure the controlled variable, which is C here. So, and then I'll make it red. So look right here. So this is our measurement of C. Measuring C, the controlled variable. So what we've done is put in a salt concentration analyzer inside the tank, and it measures the concentration of C. So ideally, I would put this salt concentration analyzer here. So I'm being a theorist here, and according to the well mix assumption, the concentration of salt in the tank at every point in space in the tank is equal to the concentration coming out here, so it doesn't matter. But ideally, you would put the salt concentration analyzer here. It's a little bit of a side note. So we're measuring our control variable, and this salt concentration analyzer then spits out a milliamp signal. So this is a current, an electrical signal. So this here is the electrical signal. Maybe I'll use this. Yeah. So let me highlight this. So this means, whoops. This is an electrical signal. That means that it's electrical because it has those dashed lines. Electrical. All right, and the electric signal is then sent to the feedback controller, which receives a set point. So here's your set point. So how salty should the water be, right? And the feedback controller compares these two, right? It compares the set point, so what it wants the salt concentration to be, to the measurement, which is what the measured salt concentration is. And based on that error signal, based on comparing them, then the feedback controller takes action by putting a pneumatic signal, a signal of air of a certain pressure from 3 to 15 psig onto the control valve, and it pushes on a diaphragm to open and close the control valve, which in turn influences this. So let me write some of this out. So this is a pneumatic signal, and that's why it has these dashes through it. So this is pneumatic. That's a pneumatic signal. This is an electrical signal. Okay, let me draw these with a different color. Okay, so what will happen is that the measurement of C, this is the measured concentration, and the set point are compared by the feedback controller. So, and that gives you an error. And then based on that error, the feedback controller takes action. And so that's this right here. So feedback controller adjusts the manipulated variable. All right, so those are the two key features of feedback control. You measure the controlled variable, and then the feedback controller adjusts the manipulated variable accordingly. And again, just as a thought experiment, let's say that W was way too high, so much higher than usual. Then the salt water would be too salty, right? And whenever you measure the salt concentration in the tank, it would measure a value that's too high than you want, much higher than you want. And the feedback controller would take action so as to open this control valve, increase the flow rate of pure water in order to dilute this salt. Oh, great, my neighbor is mowing. So that's what that noise is. Okay. So, in contrast, in a feed-forward control strategy, remember what we do is instead measure the disturbance variable. So, where that's happening is right here. So we measure the disturbance variable. Which is W. And so we have a camera here, then analyzes the size of the salt granules, and tries from that to determine the mass flow rate of salt coming into the tank. So think of this as a measurement of W. And the feed-forward controller, which also takes in a set point, so I should have a CSP here, then considers what the set point of the salt concentration is. It looks at what the actual flow rate of salt granules is at the moment, and based on that, takes action by sending a pneumatic signal to the control valve, which then opens or closes this valve. So again, right here is where, I want to use the same words as before, the feed-forward controller is adjusting the manipulated variable. So it still adjusts the manipulated variable. Which is Q. Right? And then Q. Yeah. So we're measuring the disturbance variable and taking action on the manipulated variable. And so again, let's consider a thought experiment where the salt flow rate W is way too high. Then the feed-forward controller will see that. It will be fed this input, this measurement by the camera. And based on the set point, if the salt granule are flowing in way too fast, then it will open this valve and dilute this salt concentration in order to maintain C at a set point. Okay, so now let's talk about why you might want to use one over another. So we'll talk about the pros and cons of a feedback and feed-forward control strategy. So let's start first with the feedback control. So one bad thing about feedback control, and I'll make that with a red minus. One bad thing about it is that no corrective action is taken until a process upset has already occurred. Okay? And you know that because if you look here, there's no way that you can know. Well, basically, it never takes action until there's an error here. So it never takes action until it receives a signal from the change in the salt concentration. And by the time the salt concentration is changed, it's too late because this salty water is exiting here. And so ideally, you would want to anticipate changes in the disturbance variable and take corrective action before it upsets the process. That's what feed-forward control does by measuring the disturbance variable. But that's a huge minus of feedback control. So no corrective action. Is taken until a process upset has already occurred. Okay, I think I spelled occurred wrong. Let me Google that. Okay, two C's. And that's because you're measuring the control variable, and you'll never know. Basically, the only time you can take action is whenever you see a deviation from the set point. And so controller decisions are taken after the fact. Of a disturbance upset. That is, the concentration of salt has to deviate from its set point before action is taken. So that's a minus. So a plus sign. So a positive thing about this feedback control compared to feed forward is that corrective action is taken regardless of the disturbance. For example, this here is disturbance number 2. And it is a troll. And this troll is dumping salt granules into the tank, right? And the thing is that even though we might not have anticipated this disturbance because the disturbance area we were considering is W here, right? It effectively doesn't matter where the disturbance comes from. Your feedback controller is going to measure that deviation in the salt concentration and then take action, right? So it doesn't matter what the disturbance is. You don't even need to know what the disturbance is. The feedback controller is going to take action regardless whenever your salt concentration deviates from the set point. And we'll contrast that with feed-forward control in a moment. So one more plus of feedback control is that there's a minimal need for an accurate process model. So you don't need to have an accurate model for the dynamics of how W and Q affect C. And that's a huge plus as well. So accurate model, minimal need for an accurate process model. Except for whenever we want to design and tune the controller, then it would be nice to have an accurate model. I'm just trying not to demotivate you from paying attention to process dynamics. So I won't even write that down because it's still true. There's a minimal need for an accurate process model, but having one will not hurt you. It will help you in tuning the controller. And it's sort of difficult to see why this is a plus or why this is true at this moment, but later on in the class that will become clear. Okay, so let's contrast this with feed-forward control, okay? So feed-forward control, the huge plus is that it's called anticipatory control. You measure the disturbance variable, and the idea behind measuring the disturbance variable is to take action before that disturbance variable can upset your process. So, put that in quotes, it's often called anticipatory control. This is feed forward. And that's because corrective action is taken before the controlled variable is perturbed. By the disturbance. In other words, the controller decision is made before the process is affected by the incoming disturbance. And that's great. Yeah, so that's a wonderful part of feed-forward control. And it makes total sense, right? So if you know that the salt granule flow rate is going to increase, if it's increasing, then you know that you should take counteraction right away before you see that water get a lot saltier than you want it to be, right? And so that makes total sense. That's anticipatory control. However, there are a few downsides to feed-forward control, which actually makes it less common than feedback control. And so one of these is that the disturbance must be actually measured, okay? So the disturbance must be measured, and often it's difficult or impossible to measure the disturbance. So this is often difficult or impossible. All right. So a huge minus with this, another one, is illustrated in the figure to my left. So now let's consider our troll again, right? So here's our troll. And the troll is dumping salt into the reactor. And it turns out that the feed-forward controller is only measuring this disturbance, and that's the only input it gets, right? So it doesn't know about this disturbance here, the troll. It doesn't know about that, so there's no way that it can take corrective action for this disturbance, the troll. And in fact, the salty water will get saltier as a result of this troll. So that's a huge minus. So corrective action is not taken for unmeasured disturbances. And so this is illustrated here. So the troll on left successfully upset the process. So the feed-forward controller cannot counter this troll, but in feedback, the feedback controller can handle that troll. Okay? And there's yet another minus about feed-forward control. The other minus is that we require an accurate process model. And the reason we need an accurate process model of the dynamics is to predict how the disturbance and the manipulated variable will affect the control variable exactly. Well, not exactly, but to a good degree. And then we can properly compensate for the effect of the disturbance by adjusting manipulated variable just the right amount. Okay? So we need an accurate process model. Requires accurate process model. By process model, I mean of the dynamics. Process model of how controlled, the disturbance and manipulated variables how these affect the controlled variable. So we can properly compensate. For the effect of the disturbance. By adjusting the manipulated variable. Okay, So feed-forward control sounds wonderful because it's anticipatory control. It's very intuitive. You want to take action before an upset occurs, right? But then no corrective action will be taken for disturbances that you don't measure. And you need an accurate process model to even know what to do. How do you open that valve? In contrast, in feedback control, the great thing about it is that corrective action is taken regardless of the source of the disturbance, and there's a very minimal need for an accurate process model in order to know how to open or close the valve based on the measurement of the salt concentration. And the downside of feedback control, of course, is that by the time you take action with your controller, the process has already been upset. The water is already too salty or not salty enough. And so we can't have the best of both worlds. In fact, in industry, a lot of times feedback control and feed-forward control are used together so that you can take anticipatory action in anticipation of how the disturbance will affect the process, but you also take action for disturbances that aren't measured. So you can combine these two. But feedback control is much more common. Okay, so that concludes our introduction to process control.